Hello, in this particular segment, I'm going to go over one of the kinetics free response problem. This is actually question number 45 from the practice packet. It covers most of the components related to kinetics in different sections of that question. I might break it into a couple of segments because otherwise it will be too long. So let's start with the first part of it. Basically, given the experimental data, how to use the data to derive the rate law. So this is the question, 2NO plus 2H2 giving N2 plus 2H2O. And you are given 5 experimental data performed with the different concentrations of NO and hydrogen. So in order to find the rate, the effect of the rate of hydrogen on the overall rate of the equation, you have to pick 2 experiments in which nitric oxide is kept constant without changing the concentration, and the hydrogen concentration should be changing. So if you look at experiment number 1 and 2, you can clearly see the NO concentration is remaining the same, but the hydrogen concentration is doubled. So on the rate column, you can clearly see that the rate is basically changed from 1.8 times 10 to the power minus 4 to 3.6 10 to the power minus 4. When the concentration of hydrogen is doubled, the rate is also doubled. So they are going in the same proportion. So that means with respect to hydrogen, the concentration effect is doubled, the rate also doubled. So with respect to hydrogen, it is a first order reaction. So that's what we did here. So when you try to do it mathematically, so from experiment number 1 and 2, so we picked the ratio between those 2 experiments. I usually keep the higher value on the numerator so that it's easy to solve the math. So R2, rate of experiment number 2 over rate of experiment number 1, R1 equals. So I put the values, basically substituted the values. So 3.6 10 to the power minus 4 divided by 1.8 10 to the power minus 4 equals. Now I'm coming up with a hypothetical rate law for that equation. So it should be in this format, K, rate constant, times NO concentration to the power X. We don't know what the X value yet, and times H2 concentration to the power of Y. Similarly, on the denominator, the same with respect to the experiment number 1. So you have K times NO to the power X times H2 to the power Y. So when you simplify that, you can see that this part R2 over R1 is 2. K gets cancelled because the rate law is the same, rate constant is the same, and NO to the power X over NO to the power X, because it's the same concentration for the NO, 0.06. So that factor also gets cancelled. And now you end up with 0.02 to the power Y over 0.01 to the power Y. When you simplify that part, you get 2 to the power Y. So what should be the value of Y so that you get 2 equals 2 to the power Y? So Y should be 1. So that's why when the concentration doubles, the rate also doubles. So that basically indicating order with respect to 1. So with respect to hydrogen, it is first order. Now, if you have to calculate the rate with respect to change in concentration of NO, we need to change the concentration of NO while keeping the hydrogen concentration same. So we selected experiment number 3 and 4 from the data. So I kept R4 over R3 because R4 value is larger. So 1.2 10 to the power minus 4 divided by 0.3 10 to the power minus 4. I kept the rate law equation in the same format, K times 0.02 over Y to the power Y times 006 to the power 1 divided by K times 001 to the power Y times 006 to the power 1. So this part cancels, K cancels, so you end up with 2 to the power Y when you simplify this 002 over 001. So that gives you 4 equals 2 to the power Y. So Y should be 2 in order to equalize both sides. So that means with respect to NO, this order is 2. So you can clearly see that the rate is actually quadrupled when you doubled the concentration of NO. Okay, so that's an indication. When the rate is quadrupled, that means with respect to that particular reactant, it is second order. So we already calculated the order with respect to NO and hydrogen. So now it is time to write down the rate law. So rate law format, R is equal to K times NO to the power 2, H2 to the power 1. If it is 1, you don't have to really put that 1 as the exponent. So this is the rate law for the overall reaction. So the overall reaction is 2 plus 1, which is a third order reaction. With respect to each component, it is second order with respect to NO and first order with respect to hydrogen. Okay, let's continue to the C part of the question. It's asking to calculate the rate constant K for this particular reaction. So from the rate law equation, we can see that K is equal to the rate over NO to the power 2, hydrogen concentration to the power 1. So you can pick any experiment as long as you have all the values in that row. So I just picked the first experiment. So I'm substituting the values. The R value is 1.8, 10 to the power minus 4. And the NO concentration is 006 square. And hydrogen concentration is 001. So that gives me 5,000 moles to the power minus 2, liter square, minute to the power minus 1. So that's the rate constant for this particular reaction. So once you have the rate, you will be able to calculate K using any specific experiment from the data. Now moving on to experiment number, part D of that experiment, same experiment. It's related to experiment number 2 in that list of experiments. So it's asking, calculate the concentration of NO remaining when exactly 1/2 of the original amount of hydrogen has been consumed. So when you look at that equation, you can see they are reacting in 2:2 proportion, that means 1:1 proportion. And the hydrogen concentration initially is 0.02. Actually, there is a typo here. I'm correcting it. This is actually 0.001. So we started with the 0.02 moles of hydrogen. So when exactly half of it is reacted, that means 0.01 mole of hydrogen is reacted. So based on the stoichiometry of the reaction, you can see that same amount, 1:1 proportion, 0.01 mole of nitric oxide, nitric oxide will also be consumed along with the hydrogen. So what is remaining with respect to the original amount of nitric oxide? So you started with the 0.06 moles of nitric oxide and you take away 0.01, which is reacted along with the moles of hydrogen. So you left with 0.05. That's the remaining amount of NO at that point. In experiment number 5 from the data, it's asking for the missing concentration of hydrogen. So what I did is I plugged in all the values into the rate law. So the rate is 0.8 10 to the power minus 4 is equal to K, which is 5,000 times 0075 square times H2 concentration. And basically solve for H2 concentration. So it came around 0.00028 moles per liter. So that's like a direct substitution. So this is section F of that problem. So we determined that the rate law is equal to K times NO square H2. And in this particular question, it's asking you to identify the elementary step and rate determining step consistent with the stoichiometry of the equation. So we can clearly see the three steps. The first step is a reversible equilibrium. The second step and third step are normal one-way steps. And we can also notice that N2O2 is formed in the first step. Because it's a reversible step, it is being decomposed backwards to produce NO, or it could be reacting with the hydrogen to produce H2O and N2O. So N2O2 is an intermediate. Unfortunately, we cannot really determine the concentration of an intermediate, so there is no way we can put that in an equilibrium, a rate law expression like this. Because without knowing the concentration, we cannot really substitute that. So N2O2 is starting in the second step, and it is creating another intermediate N2O, which you can see being reacted with the hydrogen in the third step. So N2O is also an intermediate. Now, another important thing we need to remember in this kind of scenario is whenever you have a rate law equation, the components in the rate law equation, for example, in this case, you have two molecules of NO reacting with one molecule of hydrogen. So those three molecules should be in the rate determining step, which is normally considered as the slow step of the mechanism. So when you look at the step 1, 2, and 3, in first step, we have two NO molecules, which is matching with this part of the rate law, but there is no hydrogen there. And those two NO molecules are producing an intermediate. So it doesn't really look appropriate for the rate determining step. In the second step, you have the hydrogen, but there is no NO. But you could replace this N2O2 from the first step. Okay, that I will explain in a minute after looking through the third step. In the third step, what you can see is N2O2 is again an intermediate, so you cannot have the concentration of it. And it is produced in the second step, starting with another intermediate N2O2. So that doesn't really work. But even though hydrogen is there, along with N2O2, there is a chance that you can substitute N2O2 from the first step because it's a reversible equilibrium. Whenever there is a reversible equilibrium, we have a dynamic equilibrium existing. So there is a chance. So I would consider the step 2 as the most appropriate elementary step, or the step determining the rate law, slow step, just because that it has the hydrogen in it, and I see that N2O2 can be substituted from the first law. So I'm going to say that second step is the rate determining step because it has hydrogen in it, and I could replace the N2O2 from the first step. So based on the second step, my rate law should be like this: K times N2O2 times H2. Now I'm trying to find a proper replacement for N2O2. So for that, I'm going back to the step 1 equilibrium. So because it's a dynamic equilibrium, I can say that rate of the forward reaction is equal to rate of the reverse reaction. So K1 NO square is equal to K inverse N2O2. That's for the reverse and the forward reaction. So from here, you could get N2O2. So I can see K1 over K inverse times NO square is now equal to N2O2. So I'm going to replace the N2O2 in this equation with this whole block. So that gives me R is equal to K1 over K inverse NO square H2, which is basically the experimentally determined rate law, because K1 over K minus 1 is just another constant. So I could easily replace it with the K. Now I have my experimentally determined rate law. So my assumption was right. Step 2 is the rate determining step. Based on the rate law from the step 2, I can substitute for N2O2 from the step 1. And I have the experimentally determined rate law matching up with what I derived.